Alright, silly people, here's the situation. We're doing another new integration method, as per the usual. But this time we're going to be basically doing the trapezoidal rule, except, and we're going to be changing the amount of steps that we're going to be sampling from as we go along to match a certain accuracy by literally taking the integral, the integrand, and splitting it up into half, and if that's not enough accuracy, then you split it up into half again, and if that's not enough accuracy, on and on, recursively until you get the value of the integral that you like. So we're just going to follow through the steps that are outlined in the problem, kind of, to try and do this. And the first step is to, of course, write a function which calculates the integrand, which for us is going to be sine squared of x divided by x squared. So I'm going to go ahead and import numpy as np, define f of x to be returning the sine of x squared, and then you divide that by x squared. And this is an interesting one because if you plug in x equals 0, you're going to get a singular point. You're going to be dividing by 0, so you should get infinity. But we can work around that by creating an if statement where if x equals 0, then the function will just return 1. As, again, Newman suggests in the problem statement. Otherwise, it just returns the function as written. Right, so that's cool. Then he wants us to define a function called step that takes the arguments x1, x2, f1, and f2, those being the beginning points, the end point of whatever trapezoidal integral you're doing, the function evaluated at that starting point, and then the function evaluated at that end point. And there is a reason why it's kind of defined that way, taking, results as arguments, and we'll get to that in a second, but we can just do that. So def step x1, x2, f1, f2, and so it wants us to basically calculate two trapezoidal rule integrals, one with n equals 1 slices and the other with n equals 2 slices. So to do trapezoidal rule, you take your h to be the first or the second point minus the first point. You divide it by the number of slices. In this case, it's 1. And then you would do I1 is going to be just your h times your function called to the first point, so f1, plus the function called to the second point, so f2, all divided by 2. And that's the entire trapezoidal rule integral for 1 slice. We do need to do 2 slices, so also we're going to recalculate h here to be x2 minus x1, this time divide by 2 because n equals 2, and then you calculate I2 from that. Again, you just use the first bit that I used there, h times f1 plus f2 all over 2, but then you add on a term which is like a trapezoid that is in between the first point and the end point, and that you can get by saying h times f of a, not a, but x1 plus h times the, it's just x1 plus h. Yes, okay, now that is fine. At this point, you can calculate what the error on this is. The error is going to be the result of the 2 slice integral minus the result of that 1 slice integral divided by 3. And you can make your decisions based on what error you get. We do want to get an accuracy of 10 to the minus 4 just from up there from part A. So I'm going to create a variable outside the function. It's called accuracy. Set it to 10 to the minus 4, so 1e minus 4. And we'll create a Boolean inside the step function, which is going to say if error is less than or equal to your desired accuracy, then you can just return I2, and then the integral is done. Otherwise, you're going to have to split it up further. So in that case, you do have to create a split between the two functions. So a halfway point between x1 and x2. So that we can just have split equal x2 minus x1 over 2. And then we need to recur this function here twice. We're going to be adding up the step function evaluated between x1 and a new x, which is going to be x new equals x1 plus the split. So then you return the first part of that, which was step of x1 x new f1 f new, and I better define the variable f new equals f of x new, obviously. And then you add on to that the step function x new comma x2 comma f new comma f2, right? I know that's a lot, but that's pretty much what he's talking about in the problem statement. That is the exact sort of method he's talking about. He does go on a little bit in a hint section in the problem statement about getting it to an even higher accuracy by calculating the error using a Simpson's rule integration in the middle of that. We're not going to do that in this video because that's just a little bit out of the purview of the problem, I think. This is just about trapezoidal rule, so I think doing it this way is fine. But yeah, once it returns that, it should be good to go, and you can even print out what the value of the integral is, which we know is going to be between 0 and 10, using f of 0 and f of 10 as f1 and f2. And I know what the value of the integral is, so I'm going to go ahead and run it to make sure it is accurate to that. And I think I actually messed up. Oh, I actually just needed to put an absolute value around the error in the if statement to get the correct value of 1.518. And I did check that with a different numerical method, so that is a good value of the integral. So part B, why does the step function take not only the positions x1 and x2 as arguments, but also the values f of x1 and f of x2? And that's because whenever you put it back into the recursion, you don't want the arguments of a function call to be a function call. That's going to create a lot of strange behavior, because whenever you call the function within the function call, whenever it recurs back again, it's going to call the function in itself. If that doesn't make sense, it doesn't make sense to me either. It's literally going to be calling the input. You're gonna be calling the function using the output of the function, and it's just going to be odd. So doing it like this, where you define all of your function calls as variables, and then plugging it into the recursion, is the way to go for sure. And then Next bit is to uh, modify the program to make a plot of the integrand with dots added showing where the ends of the integration slice lie. Um, to do this, all we have to do is we can create. Well, first of all, we need to import matplotlib pyplot as plt, just so in the part of the function where it's actually returning the value of the integral, you can do a scatter plot, which is going to show x1 and x2, whatever those values are at this point, plotted against f1 and f2. Right. So that's cool. And then after the function is done running and it's printed out the value of the integral already, we can have it do a bunch of x values from 0 to 10 using the linspace function from NumPy with 10,000 points in between. Not 10,000, but 1,000. Just create an output list, which I'm going to call FLS, and then just for x in XLS, append FLS with f of x. And again, that doesn't have anything to do with the integral. We're just plotting the integrand pretty much, so that we can get something that looks pretty like this. And let's even make it so that each of the points along the integral are the same color. I'm going to make them all red so that your plot will look like that. You can see that the dots are further apart for parts of the graph that are more linear, but then they're closer together for the bits where the plot is more curvature. So it's curving here, and so the plots are all close together, but here it's pretty much a line, so it's getting further apart here as well. So that will check out with how trapezoidal works in theory. So yeah, that's it.